It's Friday, that's nice, but I'm told, at least from the movies, right, that the closest a guy can come to feeling what it's like to be pregnant, you know, and have a baby is supposed to be kidney stones. I mean, it's supposed to be the jokes and stuff. But so if you eat a lot of, what is it, sugary stuff or chocolate, the point is stuff with a lot of calcium or oxalate in it, right? Those two. All right, get kidney stones. Well, you could, I guess, eat as much as you want. Just make sure you drink a lot of water, right? And you're going to be fine. Okay. Those poor guys who are outside working all the time and gals. Okay. But that's just, it's a common ion effect problem. That's why it's there. So we've kind of already, in fact, the quiz was a common ion effect problem, but we have silver hydroxide. How could the solubility through the common ion effect of silver hydroxide be decreased? How could you make this stuff less soluble? Ricky, what would you say?
Initial what?
How could you make this less soluble, silver hydroxide, through the common ion effect?
I guess you could probably dissolve more stuff in the solution before you...
More specifically, more common ion. You don't have any choices here.
Yeah.
Has to be what or what?
It has to be either lead or chlorine. Oh, we're talking about...
Oh, you're not, okay.
Oh, I'm sorry. I thought you were talking about outside.
Right.
More silver or hydroxide?
Yeah, more silver or more hydroxide, right? So it can't be really anything. Just more silver, more hydroxide. That would mess it up. However, you can also use the common ion effect to increase the solubility, right? A positive thing. Kelly, how could that be? How could the ion effect be used to increase, to get more silver hydroxide to dissolve? You have to have less silver or less hydroxide, right? So how do you do that? How do you achieve that? I can see two ways. Well, more solvent's going to, yeah, I guess that would work. That would work. You get some more dissolve. But that more solvent wouldn't really increase the solubility, though, because solubility is concentration. So you'd end up with the same solubility because it's an equilibrium issue. You could add something that would do what with the silver? Like Kelly gave us the idea. You got to remove these things. So add something that will precipitate the silver, okay? Or you can add a what and it'll react with the hydroxide? An acid, right? So there's two ways that you could remove either the silver or the hydroxide and in effect increase the solubility. And that's the common ion effect game. For example, the KSP for lead chloride is 1.7 to 10 to the negative 5. What's the solubility for this compound? So, Sabina, what do we do to figure this out? Set up that ice table. Okay, so, and what's my reaction, Monica, that you would write?
PbCl2 solid.
Perfect.
The arrows that go both ways.
Yep.
And then the Pb plus 2, and then plus 2 chlorine.
Yep. And she said the arrows that goes both ways. I like that. I'm too lazy to do that. But Jeffrey, now what?
Put a line through the solid values.
Yeah. Good. What else would you do? What would you do now, Marlena? What do you do next? Anybody help her? What would you do next? Yeah, she put dashes in the first row. That's not going to happen down here, though, right? Okay. But the change row, you would put what, Andy?
The change row, you have to put plus x for PB.
Yeah.
And plus 2x plus 3 out.
Perfect. Seen it with x and 2x down there. So I guess it'd be 1.7 times 10 to the negative 5 would be equal to, you'd say what, Ida? 1.7 times 10 to the negative 5 would equal what expression? x times 2x all over 1. We just forgot one thing. What did she forget? Squared, yeah. Don't forget to square it. Okay, so you end up with 4x cubed. And what's my x? Let's see who wins here. So divide 1.7 times -5, divide it by 4, take the cube root, and you get 0.0, oh, thanks, 0.016. And the units are? Big M. Good. They didn't specify, so let's just leave it at big M. Okay. Now, Gloriana, you've got like 10 seconds left on the exam, and you would expect in part B to get an answer that's bigger or smaller than part A. Smaller. Yeah, so you have time at the end of the exam, especially, check over that kind of thing. You better get an answer that's smaller for this part. So everything is exactly the same. All right, you make your ice table. Jeff said do all dashes for the solid. And then Melissa, what is this good for? 0.1 molar sodium chloride? Under the CL. Do I put 0.1 or 0.2? Because I've got a 2 here. 0.1. Because that's the initial concentration of chloride. Good. Dashes. Still have our x's and our 2x's. All right. So then we got down to same expression. All right. But now we're supposed to hopefully be able to do what?
Drop the x.
Yeah, now drop the x. Which x? The one inside the parentheses. Right, because this is, x is supposed to be really tiny. We're 10 to the -5. So it's really tiny, so we drop the x. And let's do the full calculation to make sure we can drop the x. So that's 10, this should be 100. This should be 1.7 times 10 to the -3, right? But man, I'm so bad doing stuff in my head. Is that right? It is? Okay, Sabina says it's right. Good. Okay, so is 1.7 times 10 to the -3 smaller, a lot smaller than 0.1? Well, about 100 times smaller, so I guess it's okay, right? You're getting borderline there. But if you want to get an exact answer, you should do the quadratic. That's why this 10 to the -5 is the borderline. 10 to the -6, great. -7, -8. I'm talking about for this KSP. Where'd it go? Right here. That number, -5, is kind of borderline. So otherwise, we'd have to do full quadratic. Like if this said 10 to the what, you'd have to do full quadratic. 10 to the -3 especially. 10 to the -4, calculate it and see, I guess, right? Because a lot of times you have things squared, and that really helps out. Okay. Complex ions. There's a lot of anti-tumor drugs that are complex ions. Okay. Effect of complex ion formation on solubility. I just copied this from the book. Here's a KSP reaction for lead iodide, the solid going to its ions. And it's kind of interesting, this observation. They say that at high concentration of iodide, more lead dissolves. It shouldn't. It should be the other way, right? If more concentrations of iodide, it should be that Le Chatelier's principle and common ion effect, you get less. But you get more. So what's going on? Well, you have all these complex ions, they're called, in solution. And notice how there's no S written anywhere. Complex ions. There's all this stuff is written in the expressions, in the equilibrium constant expressions. So, and what I think is kind of interesting here is that here's your complex ions, right? And And then you can write the expressions over here, the equilibrium constant expressions. And all these guys are numbers, right? These formation constants, they're all numbers. But it's this whole idea of simultaneous equilibria. All this stuff is going on at the same time. So if you could pick any one of these equations and solve for, I don't know, solve for the iodide concentration. Well, that's the exact same iodide concentration in expression beta 2, expression beta 3, expression beta 4. They're all simultaneously valid. So it doesn't matter, you don't have to start anywhere in here. They're all, you see the concentration of iodide, it's the same concentration of iodide in all those other expressions. Does that make sense? So there's no magical way to solve these things. You just have to plug and chug. All right, look at that. There's 1, 2, 4 equations. Hopefully 4 unknowns. Otherwise it can't be solved. Complex ion formation reactions have tabulated equilibrium constants called, starts with an F. Oh, Jackie, what do they call those things? Starts with an F. It's kind of silly, right? Formation reactions, formation constants. What symbol are they going to use? Beta. Okay, that's not very good. Beta. Beta. Okay, complex ion formation reactions are always written in the form. Just like the KSP, you have to know how to, know the form to write the reaction. Kimberly, for complex ion formation reactions, where do you put the complex ion? On the product. Yeah, the big hint is up here up on top with all these betas. Look at them. The complex ion is always being formed. That makes sense. It's a formation reaction, right? So the complex ion goes over here, and its ions on this side. Okay. So here's our first problem. The cumulative formation constant for tin chloride in 1 molar sodium nitrate is 12. Beta is 12. Find the concentration of tin chloride for a solution in which the concentrations of tin and chloride are both somehow fixed at 0.2 molar. Brandy, any idea on how to start this?
For the ice table?
Yeah. Ice table sounds good. This makes sense. You could try it, right? Why not? And that's our tool that we have. If we're going to do an ice table, we need a reaction. What reaction would we make an ice table for? What, Desiree? I can't hear you. SNCO2. What's the words for it, though? The what reaction? Not solubility, but Andy, there's an F. The formation reaction, right? So if I want to write the formation reaction for tin chloride, Naya, what would it be? Goes on which side? Ooh, someone said, right? Always on the product side. SNCl2. Okay.
And then on the other side is Cn plus 2Cl.
Yeah. Okay. Marlena, now what? All right. What are the values? What would you put in the initial row? Both tin and chloride are both somehow fixed at 0.2. All right. We kind of had a problem like this last time, and it's confusing. That 0.2 is what? It's the equilibrium concentrations. It's fixed there. So yeah, you can write 0.2 here, but it's kind of confusing because it's really down here. It's the final concentration. Somehow they fixed these guys at 0.2. Somehow they did that. That's what it says. Something should be bugging you here, Sabina. What about this sodium nitrate? Right, aren't we used to, whenever they give you something, you got to use it? Do we do anything with that? There's nothing. It's just, and you're going to see that a lot in the homework. They like doing this. To make it real life scenario. It must be a component and an environment that's necessary to fix those concentrations. I don't know. It's odd. But you really, there's no place for you to put it because look, sodium and nitrate, there's nothing there. Don't worry about it. Okay. So with what we've got now to work with, Monica, now what would you do? Cross everything out. I'm not sure what you mean. How about write the what the heck? Write the formation constant. Right? Beta is the formation constant expression. Right? And then we can substitute it in. I guess we didn't put an X in here. We should have put an X, right? If you want this to finish our table, it should probably look like that. Right? We really didn't need a table. Well, we'll see that, but that's okay. How would you write the formation constant expression, Jeff? Because we know the beta is 12, right? We know that guy's 12. That's equal to what over what?
Would it be x over 0.2?
Okay. He said, would it be x over 0.2 times 0.2? Before we do that, let's write it write it in terms of brackets with concentrations. Would there be anything on top? Right? Would this tin chloride be up on top? Yeah. I did it purposely lazy-like because we should be writing a what subscript down here? Aqueous. We're used to, thinking of, solids and things, and no, it's aqueous. It's a complex ion. Right? It's aqueous. It's hydrolyzed. It's in solution. So that has this concentration all over tin and chloride squared. So sometimes you can save a little trouble if you write this formation constant. So it might keep you from screwing up, making a mistake. So then we can 0.2, 0.2. Did I miss anything? Squared. Okay. So essentially, it looks like 12 is x over 0.2 to the third. But either way, I'm going to have to take 12 times 0.2 to the third. I'll get my x. I got about 0.096. That's my x. Is that my answer? Andy, is that my answer? 0.096?
What's your answer for beta equals to 12?
Yeah. What do they want you to find? Concentration of tin 2 chloride. Look in the ice table. The answers are all in the E row. So the answer is X. So that's right. I guess you should put units on it though, so you don't lose any points. Kimberly, what units should you put on there? Big M. Okay, big M. All right, I wanted to get to this because no one likes these except Ida. That's why we'll ask her about them. We're given the following equilibria. Calculate the concentrations of each zinc-containing species. in a solution saturated with zinc hydroxide. And that's a solid. See a little S on there? So that's why I say solid. And containing hydroxide at a fixed concentration of 3.2 times 10 negative 7. So each zinc-containing species, Ida, would be this guy, this guy. Well, he's a solid, so I guess I can't circle him, right? But this guy, this guy. There's like four guys that we have to solve for here. Their concentrations. So where could you, do you have a suggestion maybe where to start? All right. Any idea? Anybody help her out? It goes to me, it goes to, I know it doesn't look like it, but if you have, I circled them, if you have 4 equations, well, sorry, 1, 2, 3, if you have 4 unknowns, how many equations do you have to have? 4. And it doesn't look like we have equations, but we do. We can write the KSP equation. We can write this guy's expression, right? You know, products over reactants, products over reactants, products over reactants, products over reactants, right? So you have, it should work. You have 4 equations and you have 4 unknowns. The trick to it, though, is to start with the right one. If you start with the right one, it's a lot easier. I don't know if you remember playing this game. I don't know what class this was, in some algebra class, right? You had to solve for x equals this, or solve for 1. You got to substitute it all into the other one, and then you solve for 1, substitute until you keep substituting until you can finally solve for something. And that will work here. But there's an easy way to start, and there's a hard way to start. Does anyone see what the easy way to start is? Start with a KSP. Why, Brandy? Because, you hear Kimberly what she said? If you start with the KSP, you can get what the Zn is equal to. Can you see it? Right? If you write the KSP expression, the only 2 unknowns in there are zinc and hydroxide. But you know the, well, you know the KSP, yeah, but, right, KSP is going to be zinc times hydroxide squared, right? You agree, right? So we'll write it out. I'm just trying to see if you can picture the big picture. Can you see that, what she's saying? If you, just by writing this one, you can get the zinc. But you have to be able to see that. Can you see that? Right? You write the KSP expression. All it involves is the solid. Well, that doesn't show up. The KSP is some number, and that's going to involve an expression with zinc concentration and hydroxide. But the hydroxide, you know, is what, Gloriana? Hydroxide concentration is 3.2 times 10 to the negative 7. So you can solve for zinc. She's exactly right. Okay. So then, now you know what zinc is, and you know what hydroxide is. Okay. Then which one would you go for next? If we numbered these. 1, 2, 3, 4. We've got zinc, we've got hydroxide now. Which equation would you go for next? Number 2. Why? Yeah, plug them into the beta expression, the formation constant expression, and solve for what? The ZnOH complex ion, right? Because that's the only one that's unknown. Do you see the game plan? So try it. Right? And then once you know ZnOH, right, it'll work out. Try it, try it, try it, try it. See if you can get this to work. But start with equation 1. And if I lost you, just ask so I can help you here. Yeah, what the heck happened? Did I screw it up? I don't have my book. I don't know. It's chapter 6. That should be a typo.
What's the typo?
Why isn't there a beta 2? Kimberly's asking. I think she's right.
Oh.
Stage 25. Yeah. No, it's not a typo. There's no beta 2. So there's a complex ion that's missing. So I guess they didn't want them. They figured this is enough
Oh, okay.
zinc species for you.
I need the KSP card myself.
That's a good question. I wonder what it is.
Neutral isn't it?
That is wonder. That is curious.
Neutral ones, even those neutral ions still are aqueous in there, right?
Maybe they have a typo.
Even though they're neutral, they still dissolve in them?
Yeah, tin chloride.
Right?
Tin chloride's they call it, isn't that weird? They call tin chloride an aqueous, a complex ion, but it's not an ion. Yeah, so they shouldn't call it a complex ion, but they do.
Not very soluble.
Now you have to look at the formation constant of it to see. But it would explain that why tin is more soluble than it should be, because the compound, the species tin chloride exists. So.
So I get the Zn plus 2 concentration from the KSP problem. Do I take that and put it in the equilibrium of the second?
Yeah, because once you solve for zinc or any ion, it's valid in every equation because they're all simultaneously.
Okay, so I don't even do the initial zinc. I just put it straight in the equilibrium, right?
Yeah, you know what zinc is, so just put it in. So for the second expression, you know what zinc is, just put it in for it. And you know hydroxide is fixed,
Okay.
so you can solve for it.
That's like a lot easier than I thought it was.
So we need zinc ONH3. Anybody get answers for these? For like the one with the complex ion with 3 hydroxides or 4?
For 3, I got 6.91 times 2 to the negative 6.
Anybody else get that? 6.91? Yeah, Melissa got it. Okay, so I bet you that one's right. Anybody else get the one with 4 hydroxides?
So 9.8 times 10 to the negative 9.
How about that? Did anybody get that? Danielle, did you get these? No? I just feel better if a couple people got it. And then did you get this one? This is making sense, right? Or did I lose you? Yes, we don't need, so we're not doing ice tables at all. We won't need to. All we're going to do is just write the expression off of each one of these. This has to be, it's always just going to be products over reactants for each one of these. Products over reactants, and it has to equal that number. So those will be our 4 equations. What the heck? Don't worry about it. Jeff, did you get the last one?
I got 8.6 minus 14.
Really?
I got that too.
8.6 of 10 to the minus 14. Mel, 3 people got 8.6 times 10 to the minus 14. 4 people got it.
Yeah, that's what I got.
Fine. This has to be it. All right. Mel, you see what you did?
I got
Yeah, okay. Okay. So that's how we play that game. Okay. A solution containing 0.1 molar chloride, bromide, iodide, and chromate is treated with silver ion. In what order will the anions precipitate? Now we talked briefly last time about a hint to solving something like this. Gloriana, do you have any suggestions? Does anyone remember? There was a shortcut in solving these types of problems.
Look at the exponents on the 10? Like,
No,
no.
no.
Outside one?
Because the answer really is the S word. The answer really is
Solubility?
solubility. The answer is really solubility. But solubility is the what and what again? It's the, to calculate it, it's the, say it, Naya. It's the X in ice. It's the, say it.
I didn't hear what you said.
Say it. Solubility is the, yeah, you got to burn that in your head because it's really going to help you on the exam. Solubility is the X in ice, right? Solubility is the X in ice. We hit that so many times last time. So that's what you should be doing. But look at all the ice questions you'd have to write. But there was a shortcut. If what? Do you remember? Yeah, for common ion, yeah. But if the format, if the chemical formulas all had the same ratios, you didn't have to do that. You could just go ahead and compare KSPs and not do any calculations at all. Because mathematically it's going to work out. Whether you go by X, which is what you're supposed to go by, or you go by the KSPs. But are these all in the same format? Look at this guy. Not the last one. He screws up everything. Since you have this last one, because just picture the ice table for this compound. You're going to have a 2x in there. And not only that, it's going to be a 2x squared, right? It's messed up. So you can't just go by KSP. You could guess, and 10 to the negative 12 is right between negative 10 and negative 13, but odds are it ain't going to work. So But if you do the ice table for the last one and calculate its solubility, you can't compare it to the other guy's solubilities without calculating their solubilities. So you have to calculate the solubility for everything is what I'm trying to get at. And the only reason why is because of that darn last one, silver chromate.
Let's just take it out.
So, but if you're comfortable doing these solubility problems, there's not that much to write. Like, how would you calculate the solubility for silver chloride? Do what to its KSP? Take the square root of it, because it's going to be x times x, right? So you pretty much just take the square root of the first three and you're done. It's that last one you got to work out, and don't make any stupid mistakes, right? And then you compare all the x's, because solubility is the, Danielle? X. She said it? Okay, okay. X and ice. Yes. Okay, so try it. Compare the solubilities, and the reason why is because of this guy. Order them in order of increasing solubility. In what order will the ions precipitate? Oh, the ions that will precipitate. So you'd want the lowest solubility first, right? Because they say in order of precipitating. So who's going to precipitate first? It's the guy with the lowest or the highest solubility? The lowest. The guy who precipitates first isn't soluble at all. So you have to order these from lowest to highest solubility. Figure out what all those solubilities are and then order them from lowest to highest. That's the answer. What you could do, I see what you're saying. How I'm, it doesn't matter. It doesn't matter. See, you could make it a common ion problem and calculate x for them all, but just, right? I would just calculate the solubility. I'm just disregarding this. I'm just after pure solubility. You're right. I mean, you could, it's just less work. Oh, we're out of time. Time flies when you're having fun, doesn't it? Right?
So we're not supposed to do the whole 0.10 molar thing. We're supposed to ignore that.
Well, you can use it, but then it's like what Kimberly said. If you use it, you definitely have to set up an ice table because now you're doing common ion effect. But it's solubility. So if you want to calculate it as a common ion effect problem, or if you want to calculate a straight solubility, either way you're going to have to calculate solubility x and ice. So I say you just because they're all 0.1 molar, so I would just calculate the solubility of each one of these and kind of not even don't even worry about that part.
And then just multiply by.
No, just get your x's.
Oh, just get the.
Just get your x's, and this is going to be your lowest x to your highest x.